Alright students, today let's talk about isometric projection. Isometric projection. So what we are going to do is, very briefly, we'll talk about the basics of theory and how to draw it. How to draw an isometric projection or isometric view. I'll tell you what is the difference from a given orthographic projection. The basic difference between orthographic projection and isometric projection is orthographic projection will only give you two-dimensional figures, and provided it always depends on the position of the solid. But let's say you have a square prism just like this, resting on HP on its base, so that in the top view you can see the square, in the front view you can see the rectangle. Right, just like this I've drawn here. Now if I draw the isometric projection of this thing, what you get is a figure like this. I'll just exaggerate a little bit so that you can see it. It's not the actual thing, but you'll get a figure like this if you draw the isometric projection. Now what is the difference between these two? The moment you see this picture, you'll get, at a glance you'll get an idea, okay, this is a square prism, because it actually gives you a three-dimensional feel, whereas this doesn't give a three-dimensional feel. That is the basic difference. Now isometric projection always gives you three-dimensional feel. Now how do you get a three-dimensional feel? You bring the solid to something called isometric position, and then what is the specialty of that position? So I'm going to change the view a little bit. Okay, this is the front view of the square prism. Okay, let's say this is front view of the square prism. Now to bring the solid to isometric position, you have to keep it like this. Now what is the isometric position? That I'll tell you later on. But this is the isometric position of a solid or a square prism which is resting on HP. Now what is the specialty of this thing? You can see at least three faces of the solid. Okay, you can see the top face, the right face, and the left face. If you keep the solid in such a way that in the front view, if you can see the three faces of the solid, that gives you a 3D view. That is the essence of isometric projection. You rotate, you bring the solid to a position called isometric position. Now what is the isometric position? I'll tell you. So isometric position is actually defined as with the help of a cube actually. Okay, so if you have a cube, so let's say you have a cube like this, and the cube is kept in such a way that the solid diagonal of the cube is perpendicular to VP. We have done this problem in orthographic projection topic, so I guess you remember this particular problem. So if you keep a cube in such a way that it is resting on one of its face corners, and the solid diagonal of the cube, the solid diagonal is the diagonal connecting this point and the diagonally opposite corner, the bottom corner. So that is somewhere your solid diagonal, and if you keep that diagonal perpendicular to VP, this is what you get. Okay, now this is how you define the isometric position of a solid. So technically speaking, if you want to get the isometric projection of any solid, all you have to do is, imagine that this is a transparent cube. Okay, so all you have to do is you keep the solid inside the cube like this, right? And then you bring the solid, keep the solid inside the cube, and bring the solid to isometric position. Automatically, if you bring this cube to isometric position, the solid which is inside the cube will also come into that position. So that is technically the basics. Before going into how to draw the isometric projection, let's talk about some more theory. So as I've said, when you bring the cube, or when you place the cube in such a way that the solid diagonal of the cube is perpendicular to VP, this is what you get. Okay, in the front view, this is what you get. Now the plane obtained here in this cube is called the top plane, and this here is called the right plane. Here you have the left plane. So essentially you have three planes in isometric projection. One is the top plane, right plane, and the left plane. So separately, if you draw, this is the top plane, and this is the right plane, and this is your left plane. All right. So have you noticed something very special here? So initially the cube was at rest. Let's say this cube is right here. So the top plane of the cube is right here, the right plane is here, left plane is here. So when you rotate the cube and place in the isometric position, all the horizontal edges, the top plane has 4 horizontal edges. All these 4 horizontal edges will be inclined at 30 degrees angle, which means this is 30 degrees, this is 30 degrees, and these are also 30 degrees. All right, and all the vertical edges remain as vertical. So if you take the right plane, you have 2 horizontal edges, one at the top and bottom, and 2 vertical edges. So when you draw the right plane, all you have to do is do it like this. The top plane is inclined, top edge is inclined 30 degrees, bottom edge is inclined 30 degrees. These 2 are horizontal edges, these 2 are vertical edges. Similarly, in the left plane, this one is 30 degrees inclined, 30 degrees inclined. These 2 is vertical. So that is the golden rule. To draw any isometric projection, all you have to do is draw all the horizontal edges at 30 degrees inclination and vertical edges as the same. Now the problem is, it's isometric projection. Now it is very much similar to your orthographic projection, which means you bring the solid to isometric position and then you take the front view, and that's your isometric projection actually. So as you can see, this is a case where the axis of the solid is inclined to both planes, which means this edge, let's say this is the edge, the pen is your edge, right? When you keep it like this, now it is inclined to HP and VP. Inclined to VP, if you place a plane like this, this is a vertical plane. Okay, let's say this is your vertical plane and this is your horizontal plane. So if that edge, if you keep it like this edge, one edge, or all of the edges are inclined to both HP and VP. Now if you know orthographic projection well, when an edge, any edge is inclined to both HP and VP, and if you take the front view, you won't get the true length of that edge. Suppose let's say this is 20 mm long or 30 mm long. That 30 mm will not be visible in the projection, that it will be foreshortened, or it will be shortened a little bit. Now our intention is to find out how much shortened. Okay, now if you see the figure, you can see that all the edges of the cube are equally foreshortened. Okay, equally foreshortened. This edge, this edge, this edge, all these edges are equally foreshortened. Now our intention is to find out how much it has shortened. Okay, so there's a method for it, right? I'll tell you. So to find out how much foreshortened, what I'm going to do is I'm going to draw the same old figure of the top plane, which is 30 degrees inclined, sorry, 30 degrees inclined. Now I'm going to take this small triangle right here. So this is 30 degrees. I'm going to draw a 30 degrees angle like this, right? Now this length is actually my isometric length. All right. Now what is the actual length of the square? If you take a square, this is actually 45 degrees, right? So what I'm going to do is I'm going to take this 45 degrees angle here and of the true length. Okay, now this side is actually the true length side, 45 degrees. So what I get is something like this. So this angle is 45 degrees. This is the true length side at an angle 45 degrees. So I'm going to take this small triangle. So this small angle is 45 minus 30, 15 degrees. Okay, the whole angle is 45. This is 30 degrees. So this should be 15 degrees. So this is what you get. Okay, here 15 degrees angle. Here it's 45 degrees. So this is 45 and this should be 45. 45 degrees angle. And you have a triangle like this. This side of the triangle is true length side and this side is isometric length. Iso length. Corresponding isometric length. So if you work out from these two triangles, if you take this triangle and this triangle, and if you try to work out a ratio, so I'm going to change the drawing something like this. I'm going to draw it like this because one side you have 15 degrees, other side 45 degrees. I'm going to change it like this. It's a little bit exaggerated so that you can see. So this is 45 degrees, right? So one side 15 degrees, the other side 45 degrees. This side is your true length side and this side is your isometric length side. So right now what you see is called isometric scale. Isometric scale. Now the good thing is, if you know the actual length of the square, let's say it's 30 centimeters, okay, oh, sorry, 30 mm, 30 mm. To find out the isometric length, all you have to do is you take this 30 mm in your scale, you measure from here to here is 30 mm distance, and then from this point, you draw a line which is exactly parallel to this line, like this, parallel to this line. So this length is your required, if this is 30, this is 30 mm, this is your corresponding isometric length. All right, now you can draw, you can make any measurements here and find out the corresponding isometric length using the scale. So probably if you have a very long length or very large measurement, or let's say if you have 5 or 10 measurements to take, so what you do is you draw a longer line, and from one side you take 15 degrees angle, draw a line, the other side you take 45 degrees angle. The length of the line you can decide, doesn't matter, you can just scale. So what you have constructed here is a scale. So this side is the true length of the line and this is actually its corresponding isometric length. So in between if you want to find out any length, all you have to do is you take a compass or a scale, you measure the distance and offset it here, and from here you draw a line parallel to this line, it will meet here, and that is your corresponding isometric length. Now another thing is, this is how you find out graphically. Now there is yet another method, like if you consider this triangle, if you solve this triangle using trigonometric rules, you can find out the ratio, actually the isometric length by true length, or this length divided by this length. You can solve using trigonometric rules and you will get the ratio as 0.816. okay, 816. So the idea is, if you want to find out the isometric length of any true length, all you have to do is you multiply by 0.816. Now coming back, if you want to find out the isometric length corresponding to 30 mm distance, the simple solution is take a calculator. 30 into 0.816 equals 24.48 mm, and that's your corresponding isometric length. Now this length is the same as this length. So basically, if you want to find out the isometric, coming back to our question was how much foreshortening happens. Okay, when you keep the cube like this, all these edges are equally foreshortened, and how much is that foreshortening, how much shortening happens? That is our intent. That was our intention, to find out how much foreshortening happens. Now this is what we have found out. The length actually shortens by a factor of 0.816. So to find out the isometric length, what you have to do is you have to either multiply by 0.816 or you construct a graphical scale like this. You offset the distance that you need to find out. Here the true length distance you have to offset here and draw a line parallel to this edge, and this length will give you the corresponding isometric length of that true length. So that's as simple as that. Now that's about the theory part. That's pretty much the theory, and you don't need to worry too much about the theory or how to find out this ratio. You can refer to the textbooks how you get this ratio 0.816. That's not a big deal. Okay, the actual situation is, the actual worry is, how do you draw the isometric projection? That's what you need to focus, right? Let's see.